to the Billy Graham Center, to Wheaton College, and to the 8th Annual Advanced Severe Weather Preparedness Training Programs. This is a unique second part, a new part of the advanced programs that we've never offered before with the Severe Weather Forecasting Conference, and I want to give a lot of credit to Paul Cervatka and the College of DuPage Weather Office for putting this together. I'm going to turn the floor over to him in just a couple of seconds after a couple of real quick administrative announcements. On behalf of Wheaton College Department of Public Safety, they've asked us to share a couple of things. One is the obligatory fire exits. You'll notice on both sides of the aisle and push-out seats. No, I'm kidding. This isn't an airplane. On both sides of the auditorium, there are fire exits as well as in the back of the auditorium. So in the unlikely event of a fire alarm, you just go out the doors. They've asked us to share that parking anywhere in the parking lots, as long as you're not parked in a handicapped spot, as long as you're not parked in a fire lane, is acceptable today and tomorrow. Don't worry about the permit required. Your ticket to the conference is your permit to park in the parking lots. We do ask tomorrow, school is in the process of closing for spring break. Believe it or not, spring break already. And there will be students on campus, but basically you should have a pretty well free reign of the parking lot immediately adjacent to the facility. You got tonight, when you checked in, an envelope marked DuPage County Office of Emergency Management, and in that envelope there are two pieces of paper. They are your lunch ticket for tomorrow and your banquet ticket for tomorrow night. Please guard those with your life. If you don't guard those with your life, then you have to ante up the cash at the cashier at the restaurant tomorrow. Those are your meal tickets. We do not have replacements for them, so if you lose them, don't come to us and ask for replacements because there aren't any. Paul will be talking to you about some things on the banquet. There are some of you who walked in off the street. We're trying to make some arrangements to get some banquets things worked out. Also, tonight, as we have refreshments, and also tomorrow when we have refreshments, it will be in the hallway as you go out the front door where you came in, immediately to my left or throughout the door alongside of the auditorium. Washrooms here on campus, again, if you go out into the lobby, hang a left, make a right turn heading toward the Billy Graham Center. Both the men and women's washroom are adjacent to the entrance of the Billy Graham Center. There are also, in like fashion, other washrooms, one floor above and one floor below. So if we get a press for everybody needing to get rid of the coffee that we give you early, you can go one up and one down, and we got plenty. There will be a pop and cookie break later this evening. There will be just plain coffee when you walk in tomorrow morning, and then we'll have coffee and rolls and things like that in the middle of the morning. So you should have no problem eating. A number of you were here today for lunch. We had a real problem right after lunch keeping everybody awake because they had so much good food to eat for lunch, so I think you'll enjoy the meals tomorrow. Without any further ado, I want to turn the podium over to Paul Cervatka. And before I step down, I want to just ask that we give Paul a big round of applause. There's a lot of work went into this conference, and Paul really pulled it all together.
Thank you. You can tell my students are the ones who are going to have brown noses all weekend. I would like to take the opportunity to welcome you here to basically the College of DuPage workshop. We weren't able to host it ourselves, so we brought it over here to Wheaton College and combined it with the program that DuPage County has offered for so many years. When I started this idea, I really had no idea what was going to happen, and just to look around and see how many people have made the trek to Chicago in March says a lot about, most of it says about the speakers that we have here today and tomorrow. I just want to give you a little quick introduction that we have students here from, I think it was 19 different colleges and universities and in 17 different states. And we'll try to do a little bit more if you bring your stuff, yay, go for, NC State over there? A lot of people from North Carolina, New Mexico, etc. We'll do a little bit more recognition of that tomorrow night at the banquet. There had been some registration misunderstandings, and I apologize if it was our fault, and if it was your fault, well, I'll overlook that too. If you did not get your banquet ticket, we probably will be able to get you into the banquet. We'll talk about that more tomorrow at one of the breaks. Those of you who, there was a wrong registration, I think everything's taken care of with lunch tomorrow. You just purchase the lunch, and that'll be fine. If there's any other problems, please feel free to see me at any of the breaks, and we'll try to take care of everything. If there's people from your group that did not make the trip, let us know, and then we can free up those lunch and banquet tickets as well. Okay, so it was kind of fun to be walking through the parking lot and see all the, well, the Weather Geek license plates that we saw out there. We'll try to be taking some pictures of them and then post them on the web at some future point. I would like just to make a quick announcement about what this is geared for. My idea to give this conference was to present to you some information that I think is really vital to understanding how to forecast for severe weather and how to understand severe weather. I've been to some wonderful AMS conferences, and those conferences have always cost a lot of money, and it's been a pain to try to get there, especially for undergraduate students. And that's where my passion is to try to bring better forecasting education to undergraduates. And I'll talk a little bit more about this tomorrow night. So I wanted to give it an opportunity to let you see some of the top speakers in the world when it comes to severe weather, top forecasters, top research meteorologists, so that you really understand what you're getting into in the field of meteorology. As a result, we've tried to gear the material to an undergraduate level. It assumes some prior knowledge of forecasting and severe weather. Some of it may be over your head. Just listen and try to learn as much as you can. We also have a number of operational meteorologists from 6 different National Weather Service offices here. And I think this is going to be fantastic information because this is cutting-edge stuff. This is stuff that may be coming out in future BAMs or weather and forecasting issues. And this is going to be really good for everyone who's involved with meteorology. And so without any further ado, I'd like to introduce our first speaker, Ron Pryzpylinski. I first met when he was in Indianapolis. I think I stopped by his office and was quite impressed with his severe weather knowledge, and then I saw him at many conferences, including Canada, and he was just passionate about all the weather that he'd like to talk about in the severe weather. And he's really been doing a lot of good studies on derechos and boeckos, and that is what he's going to be talking about tonight. He's the Science Operations Officer from the St. Charles or St. Louis, Missouri National Weather Service Forecast Office. I welcome Ron Pryzpylinski.
Thank you, Paul. I'm going to start with a little historical approach. I'm going to show you some early stuff, which I did some work back in the 1980s at Indianapolis office for starting points. We're going to begin with the slide projector. We're going to key upon boeckos and derechos for this particular talk. And I know you can see a lot of good stuff tomorrow on supercell convection. We're going to kind of key upon windstorms and also possibly some non-supercell tornadoes occurring along leading edge of windstorms and so forth. So with the first slide, I'm going to try to get this going. Nope. Where am I? Yes? There we go. We're going to focus our attention on particularly on the multi-cell evolution, particularly squall line evolution. This would be the third. Okay. Yeah. Right. On multi-cell squall line evolution, this is going to be our focus for tonight's presentation. But you can tell this is the 4 basic groups of thunderstorm types that exist: a single cell, severe and non-severe, multi-cell cluster, multi-cell line, and supercell convection. And again, you'll be looking at a lot of these images. This is from Chuck's and Al's work that they've done back in the late 1980s, the graphics with the classic supercell structures and so forth. And then the classic HP evolution, we see the very fat, wide hook structure. There'll be some presentations on this particular storm structure likely tomorrow. Well, I'm going to focus on this structure. This is the evolution of the boeckle, and this is work done by Dr. Fujita in the beginning in the late 1970s. And The evolution begins first with often a tall single cell. We observe a lot of times very intense thunderstorm, or it could be a cluster of linear line storms here. And then particularly with time, the actual burst of wind will cause the concave echo to bow out and produce this nice classic comma-shaped structure with the greatest degree of damaging winds occurring at the apex of the bowing structure. And there are times we observe even some non-supercell tornado development, vortex evolution occurring at the leading edge here and also the northern portion. This is not going to work out, so we'll go to the next slide. This is one of my early slides from the Indianapolis Forecast Office. This is the old City 4C radar, conventional radar. Used to work back in the 1980s. Very typical radar imagery you would see on the old system. Basically, this is the 5 DVIP level we observed. And this is one of my first cases I examined in 1982, May 3rd. And a line of convection, this actually formed across eastern Missouri, produced several tornadoes across the St. Louis area, moved across Springfield, Effingham, Illinois, and then propagated east-northeastward into west central and north central Indiana. What's unique about it, we focused our attention in the 80s on storm reflectivity structure, three-dimensional structure, and we spent a lot of time looking at that particular evolution here. And with time, we're going to go through a sequence. One thing we come across in this particular sequence, we see little bowing evolutions occurring to our northwest here, as well as to the west here. And you can see a little concavity, at least a little type of a present little circulation, possibly in the reflectivity field, kind of shows that little type of circulation. So we kind of focus our not only on the reflectivity pattern, but also on the echo evolution here. A little weak echo channel in the rear portion of the storm. And again, this particular storm likely had some type of circulation associated with it. About 20 minutes later, a nice, beautiful, small little comma-shaped, bowl-shaped echo evolved. And this particular storm did produce a series of small tornadoes across west central Indiana, just south and east of Lafayette, Indiana, near the town of Frankfort. And again, the big thing is these little tornadoes like to seek out mobile home parks. Never fails. Never fails. All the time. I see this happen too often. And again, this is some examples of house trailers got blown around by this particular storm. And one thing to observe the tornadic activity with that particular storm to the southwest flank there, we often see 2x4s being injected into the ground. And this is very common with tornadic activity. Another classic example occurred on March 10th, 1986. This is a really incredible case. We had a combination looking at small comma-shaped reflectivity patterns east of Indianapolis here in this case, and then classic supercell structures. So we have a variety of reflectivity structures evolving across this whole big line that evolved, which extends almost about over 250 kilometers in length here. What's amazing, in this particular case, back on March 10th, this is something we had a chance to look at the vertical structure of some of these storms. Pretty impressive, up to around 35,000 feet on this particular afternoon. But what's amazing in this case, this little comma-shaped pattern right there, a very intense tornado was associated at the comma head. Damage of highs up to F3 was recorded with that little feature. Very hard to discern in real time. I've got a line moving at speeds of over, like, say, 50 knots, moving east-northeast. Echo structure constantly changing, evolving here with time. Yeah, the ones down here were producing also some really horrendous tornadoes across the Louisville, Kentucky region. But again, this was very hard to discern in real time, these little comma-shaped echoes that we observed. And again, this was one of those classic cases. We just had blanket warnings out across the leading edge of the line here. And just an incredible case that we observed. And here's some of the damage. Again, the house trailer got blown away. And this is very common. We see these house trailers. I mean, with that little storm across east Indiana there. Some other damage. Again, more 2x4s get injected into the ground. Again, signs of a tornado coming through portions of east Indiana here. And again, in this case, we had some pretty impressive damage to a particular home here, north of Richmond, Indiana. The whole side of the house just got blown away in this particular case here. At this time, too, the chilled Doppler radar was operated on case-by-case basis across portions of eastern Illinois and western Indiana. And this was an image taken back in April 4th, 1982, showing the first signs of reflectivity, what the images would look like on the chilled Doppler back in 1982, showing conventional reflectivity images in this case. And then we also show, again, we tried to discern some of the little small-scale features with these particular storms here, the comet-shaped structures and so forth. And again, this was just the first early signs of utilizing Doppler radar. And note here, this is the velocity imagery. This is really a messy situation here. It's not really a clean pattern, but this is basically looking at the full spectrum of velocities with the chilled Doppler radar. Okay, I'm going to stop right here, and we're going to move on to the there we go. What I brought with me is a set of slides focusing upon two different squall line cases. Right now, over the past 3 years, we've done some work on squall line convection, actually particularly bow-echo convection across eastern Missouri and portions of southwest and south central Illinois. I brought with me two cases, and we're going to look at one case across the Missouri region. This occurred on July 2nd, 1992. And the second case is a comparative case. We're going to be looking at an impressive bow-echo that moved across portions of New York State, eastern New England region on July 15th, 1996. We're first going to key upon, this is some of the outline we're going to key upon. First, we're going to key upon definition of MCS. What is an MCS in this case? We're going to look at some historical studies, some excellent work done back in the 1980s by Johns and Hurt, Al Moeller, myself, Virginia, and so forth. And then we're going to take a look at the 4 stages of squall line evolution. And recent work, we're going to spend some time on some recent work done by Howes, by Eric Rasmussen. His work, he'd done his PhD work here a little bit, Klimowski and Wiseman, and also forecaster Gary Schmacher at the St. Louis office here. The MCS, the definition basically, this is from Mike Biggerstaff's definition. Mike's from Texas A&M University, and he defines it basically as a cloud ensemble of associated precipitation, lightning, wind, pressure, and thermal perturbations that are generated by a group of deep cumulonimbus clouds that develop over a mesobea scale of time of greater than 2 hours and space of 100 kilometers or greater in this case, and domain of which interacts synergistically with one another. And convective activity must last longer than the typical life cycle of an ordinary convective cloud, 90 minutes. And supercell storms may be components of an MCS. However, a single isolated supercell may not necessarily satisfy that spatial scale requirements to qualify as an MCS. In general, MCSs are comprised of groups of ordinary convective cells that form in response to environmental forcing over a mesoscale region. That's what happens when you wear a sweater tonight. Beginning with some of the early work, as I mentioned before, Dr. Fujita did some great work back in the mid to late 1978, 79. And again, he first, looking at some of the work from the Nimrod project, he was able to devise basically the 3 stages of a bow-echo. We've got the tail-echo stage, the bow-echo stage, and comet-echo stage. Again, his first thoughts were that the bulge of the line echo was a inducer of the high winds, basically. But after looking at additional data with the Nimrod project, he revised his conceptual model based on new Doppler data sets collected with the Nimrod project, and found that the actual downburst was the cause of the bowing within the line. And again, you can see how, again, we refer to it as a linear line initially developing, and then this particular storm bulges out due to the damaging downburst winds. We see this spearhead echo forming near the apex of the bowing structure, and then we see the rotating comet head evolving with time. And there are times we do observe tornadic activity, particularly near the apex and north of the apex of the bowing structure. I did a little work back in the early 1980s. And again, I kind of keyed upon echo structure. We were able to look at a number of cases across central and northern Indiana, and I was able to devise a little simple conceptual model of the mature phase of a bow echo. And the solid contours indicate reflectivities. You can see 41, 46, 50 dB Z reflectivity, the Boeing structure itself. The weak echo channel, indication of the intrusion and dry air in the backside of the convective storm. Maximum echo top displaced on the forward flank. And then again, the strong low-level reflectivity gradient noted on the forward flank of that particular storm. Other work that was done by Bob Johns. And again, most of the work was done when we were looking at storms in their mature phase. We had troubles in the 1980s trying to forecast the initial onset of damaging winds. We had problems, I can recall a number of times when I was at the Indianapolis Forecast Office. We missed the first 2 or 3 counties, or at least first couple counties, trying to capture. But once the Boeing evolution evolved, we were hitting their warnings quite nicely. Bob did a lot of work with looking at radar summary charts, and his focus was on the derecho. Basically, the derecho, its origins, it's a windstorm phenomenon which was first recognized in the scientific literature back in the late 1800s by Hendricks at the University of Iowa. Derecho is a word which can be interpreted as being straight ahead or direct. And he chose that particular word to identify the convectively induced winds. There was a big argument or discussion going on back in this time where we had the Army Corps, the Signal Corps at the time was taking a lot of weather observations, and they were classifying everything as tornadoes. No matter what type of wind damage you had, it was actually a tornado. But Dr. Hendricks basically proved them wrong, the fact that we did have, like say, clusters of intense winds causing quite a bit of widespread damage here. After looking at several radar summary charts, Bob Johns down at SPC and also Bill Hurt was able to devise a criteria to identify derecho events. And basically he looks at areas, reports consisting of convectively induced wind damage over 26 meters per second. And this area must have a major axis of over 400 kilometers in length, or 250 nautical miles. And reports must exhibit a non-random pattern of occurrence, a chronological progression within the area that must be at least 3 reports separated by 64 kilometers or more, either of F1 damage or convectively a gust of 33 meters per second or greater in this case. Of his study he looked at, he's shown that the major axis associated with derecho events, basically we see one major axis extending from Minnesota down towards northern Illinois here, northern Indiana into central Ohio. And we do observe a secondary axis across northern Missouri into southern Illinois and down into central Kentucky. Using radar summary charts, Bob Johns and Bill Hurt was able to document the large-scale radar echo patterns associated with the derechos. They were able to classify derechos into 2 groups. One's called a progressive type of pattern, basically, and the other one's called a serial pattern. Progressive is defined basically as having a short curved squall line orientated perpendicular to the mean wind of damaging winds occurring near the bulge, while the serial line is basically a squall line orientated to relatively small angles between the mean wind direction and also the squall line axis here. And here are some examples showing basically the top one showing the progressive type pattern. You see a single type Boeing structure moving along a quasi-stationary frontal boundary toward the south and east, and then we see a serial type pattern extending with basically a cold front, warm front type pattern. We observed the serial pattern a lot more in the cool season. We've been noticing this quite a bit, like say in the months of March and April, while the warm season pattern, the progressive pattern, is observed quite a bit during the time of like say June, July, and into the month of August, September. Some other good work was done by Al Moeller. He showed that, for example, a great case was the Northern Texas case. He showed in a situation where there were several HP supercell structures which developed close to the derecho's bow position and gradually evolved to take a HP bow-equal transition. And during the HP phase, each of the supercells exhibited southeastern flanks, weirs, high reflectivity hooks, and so forth. And here's Al's example. This is one of the classic ones from Texas. Occurred on May 25th, 1996. Note, for example, we see Nice broad bowing structure, yet we see several supercell structures within the bow. This is more of the HP variety, very fat, wet hook echo, well-defined B-word structure. This is a transition into, like say, more of, again, of the HP variety, and then weakening further to the north here. This particular storm did spawn an F3 tornado just northwest of Waco, Texas at this particular time. And we have these other cells are producing intense damaging winds and large golf ball to baseball sized hail in this case. I continued my work in the early to mid 1980s using conventional radar, and looking at over 20-some cases, we were able to devise 4 general types of convective storm reflectivity type evolutions with the derecho events. And these are the 4 basic types we were able to devise in the mature phase. And some of the more common ones was a type 3 type system, where we do see supercells evolving on the southern flank and a bow echo observed to the north. This is similar to what Al was observing in some of his cases down in Texas. Other cases, type 2 event, we see again the bowing structure, isolated convective cells forming downstream from the bow itself. The activity to the east and north is referred to as the warm advection wing. This is very common in some of the other type of derecho events we observed. And then this type number 4 is where we do observe an HP structure evolving into a bow echo structure. This is this is more observed across the high plains region, and again down across the southern plains. On the 2 cases I'm going to present tonight, I'm going to again focus upon the July 2nd case, 1992, and July 15th, 1995. Basically, they had extreme capes, greater than 4,000 joules per kilogram, moderate shear. We're looking at the mean shear level between 0 and 3 kilometers, around 14 to 17 meters per second. Surface features, east-west frontal boundaries was present. It could be a result of an old outflow boundary from previous convection, or it could be, again, quasi-stationary frontal boundary. Again, extreme instability in all these cases. And we have a common cooperative right now with St. Louis U. All the cases we observed, of the 10 cases here, the east-west frontal boundary was present. Could have been due to old outflow from previous convection, or it could be due to actually a quasi-stationary frontal boundary extending towards the east. You're going to hear a lot about boundaries in these several presentations today as well as tomorrow. Here's the July 2nd case, a mapping of the wind damage, as well as showing the actual positions of the squall line. Tremendous amount of wind damage occurred across Columbia. I know we have the University of Missouri folks here, Chris Ratley, and his group, likely at the time, those folks observed some horrendous wind damage at the university during the late afternoon hours of July 2nd. But most of our intense wind damage extended to the north and east from Columbia towards, this is called Audrain County, and then also Pike County, Missouri. St. Louis is down here to the east, southeast here. But this is really an impressive bowing structure which produced quite a bit of wind damage, with the greatest degree of wind damage across just south, basically, of the actual, actually to the north of the apex in this particular case here. We like to work on composite charts showing actually the upper level pattern, the upper level jet pattern, and so forth. This is one of the this is a progressive type system that moves across on the late evening of July 2nd. Pretty good shortwave trough across the central plains here, 80 knot wind max, 300 millibars across the central plains, 65 knot wind max, co-frontal boundary pushing across western Missouri at 00Z. Here's an outflow boundary from previous convection that, again, was orientated east-west across our region. 850 millibar dew points, 18 degrees Celsius and greater, pretty impressive instability. Surface dew points at 75 degrees and greater. One of the key features we look for is the pooling of low-level moisture, particularly south of the boundary. Very, very common feature we observe with these type of windstorm events. When we talk about instability, we have plenty of instability. We're 4,000. This is 00Z from Springfield, Missouri, from Monette, Missouri, or 4,500 joules per kilogram. Pretty impressive here. And note the shear profile is pretty linear. You know, we don't see a great. You'll probably be seeing a lot more examples of curve holographs in a lot of the other presentations. But in this situation, we got almost a straight line holograph within the lowest 3 kilometers, pretty straight for the most part. So it's a very common type profile we observe as a pretty linear type profile with a lot of our cases. On the July 15th case from New York State, again, note you see some similar type patterns existing here. Note the jet structure, pretty linear in nature. The upper level jet 95 knots, the 500 millibar jet 65 knots, low level jet 25 knots, all basically from west-southwest to east-northeast, basically right across the ridge axis in this region through here. Dew points again 18 degrees Celsius and greater across much of the Great Lakes region into Indiana, Ohio, and so forth. And dew points at 00Z, 78 degrees across this whole region. Very incredible. So again, we see the good pooling of moisture. A frontal boundary extending across from northern Wisconsin through Lake Huron down into Lake Ontario in this case. And again, the sounding does show a very good high degree of instability. Again, I got close to 4,500 joules per kilogram within the lowest 100 millibars from this particular sounding here. Very unstable atmosphere with this particular case as well. Okay. Now I'm going to kind of diverse just a little bit in the presentation. We're going to marry, like, say, some science into these 2 cases here. And I'm going to talk briefly about basically 4 stages. I mentioned earlier on about the 4 stages of a squall line. We're going to spend a little bit of time on the formative stage, early stage, the intensifying stage, and the mature stage and dissipating stage. I'm going to really key upon basically the intensifying stage as well as the mature stage of squalling development. Back in the 1985, Bluestein and Jane did some great work looking at convective squall lines across Oklahoma, utilizing radar data from Norman. And they found out that, again, the early stages of squalling development can be classified into 4 groups: broken line, back building, broken aerial, and bed aerial. And note most of the cases fall in the broken line category, with back building being a second closer number here. Most of our cases, we've been looking across Missouri, been in the broken area and broken line category for our cases across central and eastern Missouri. And the diagram they do show, in this case, you can see the 4 different types, how squall lines initially form, again, in the broken line evolution with time, becoming a solid line during the mature phase. The back building case with new growth occurring in the southwest flank, broken aerial, eventually this whole cluster of storms evolve into a linear convective system, and bed aerial, which this I'm not too familiar with. Basically, we see some convection forming within a larger area of precipitation. On the July 2nd case, and back in 1992, this is around 2205 from the St. Louis radar showing the reflectivity data. We have one, and this particular afternoon, I guess in Chicago you have the great Taste of Chicago, right? The great festival this time of the year, early July and so forth. On this particular afternoon, we had horrendous amount of wind damage on July 2nd, 1992 across much of Chicagoland, I think around early afternoon, 1-2 p.m. This particular cluster moved across New Indiana, and we saw new convection evolving to the southwest here. This is one of our few cases here where we have new growth forming in the southwest flank. We're going to focus our attention on this cluster to the west in western Missouri as it propagates across central and eastern Missouri with time here. A little closer view of this image. This is taken at 22:58, about almost an hour later. The radar allows us to see well-defined outflow boundaries with previous convection. This is, again, part of the new growth forming in the southwest flank. You do see a little fine line showing quite nicely, showing some intense outflows with this convective system. And here's our new growth, our multi-cell linear convective system to our west, moving towards central Missouri and also the city of Columbia. Again, I'm going to focus my attention on those two stages, the intensifying stage of squall lines and the mature stage of squall lines. Well, again, a lot of the work done in the 80s was on the mature phase. You saw a lot of the basic reflectivity patterns, the molecular evolution and so forth, but very little was done, like say, on that intensifying stage quite a bit. So I'm going to kind of keep on that part. So this intensifying stage, basically, we see a transition from the early to intensifying stages when the convective line nearly becomes a solid line echo. Reflectivity breaks begin to fill in between the cells, and the reflectivity increases. Now, a good paper came out in 1993, and this fellow's in the audience here. And I think it's a great paper. Eric Rasmussen did some work with Steve Rutledge in 1993. And he talked about this thing called a positive buoyancy anomaly and a negative buoyancy anomaly. And basically, the positive buoyancy anomaly, in this case, we're referring to basically the updraft region of the leading edge of convective line. Basically, this is due to heating of condensation, freezing the leading edge of the convective line again. We see a lot of latent heat release occurring. We see the evolution or generation of mid-level low developing, which basically is going to cause this flow to accelerate upward with time here. And the negative buoyancy anomaly referred to basically as the convective scale downdrafts due to cooling of evaporation, melting, as well as the condensation loading within the region of the origins, what's called the mesoscale inflow jet. This is Eric's diagram, and in the intensifying stage, we observe basically this flow structure. We see intense updraft region through here on the leading edge and intense downdraft region on the back edge here. And this region in between is referred to as region of negative horizontal vorticity, this whole region through here. And Eric refers basically this whole region called between the two zones of the updraft and downdraft as a rearward sloping zone of negative horizontal vorticity. And basically, we see both a positive as well as a negative buoyancy anomalies, which produces intense horizontal buoyancy gradients across this zone. And basically, this is an area where we see intense. It's like intense, like wall of water, and it just intense downdrafts. On the negative side, we see intense updrafts on the positive side through here. An intense, strong baroclinic zone exists on the leading edge of the convective line here. At the same time, Morris did some work. Morris Wiseman at Norman did some work basically, and also talked about the horizontal gradients of buoyancy which existed across this particular zone here. We talked about the evolution of the linear convective lines, which is based upon the interaction between the buoyant updraft and the storm-induced cold pool and the ambient shear. Morris's diagrams are showing this region through here where we see in the simulations, the first simulation up here is basically the convective cloud leaning down shear due to the shear associated with the ambient shear initially. And once a cold pool begins to form, we see a balance between the ambient shear and also the system of cold pool. And we see negative horizontal vorticity evolving here. And then, like say, with time, we see how this cloud begins to tilt up shear with time, where the cold pool overwhelms the ambient shear. And then the fourth stage, we see a balance forming again. We're going to show you radar imagery showing these three, this is number 2 and number 3 in this particular diagram through here. Also, at this particular time, Klimowski did some good work with the actual case, the June 20th, 29th MCS case over North Dakota. And when he found out that he observed the evolution of the mesoscale rear inflow on Doppler radars across North Dakota, and the observations did show that the mesoscale rear inflow was initiated near the high reflectivity cores of the squall line. The maximum values of the rear inflow was initially located near the high reflectivity cores. Rear inflow was not homogeneous across the entire length of the line. Strong rear inflow was located near the trailing stratiform precipitation region, and there's a slight correlation being was evolved between the development of the mesoscale rear inflow and also the front to rear flow. And this is Brian's work showing the June 2029 case. What we're looking at here is the origins of this thing referred to as the mesoscale wind flow region. Note the dark shaded region here is where we have intense winds blowing actually towards the east here in this case, if we're looking from east to west in this fashion. And note how the mesoscale wind flow eventually evolves to the west with time across a couple of the plan views here. One of our goals in our MCS study was to basically improve upon our forecasting ability to predict the initial onset of damaging winds. And we looked at this thing, this velocity signature called basically mid-altitude radial convergence. And what we're doing essentially was surveying the component of the convective squall lines sloping updraft and downdraft currents. And this goes back to the work by Rasmussen, who did his work basically looking at sloping updraft and downdraft currents here on the on the MCS's forward flank. This is very similar to what's referred to as the deep convergence zone, which Lyman Parker has documented back in 1996. Now, this deal about this mark signature, really, this idea came from the work done from the microbursts, even though we're talking about different dynamics here. But the work done by the folks with the microburst studies back in the late 1980s here, from Campbell, Eisminger, and also from Miles, they found basically, at least Mike Howitz and his group at NSSL found three important signatures to identify damaging downburst winds. One was referred to as a rapidly descending reflectivity core. Strong and deep convergence at mid-altitudes, greater than 22 meter per second convergence, and a reflectivity core that begins at a higher height. We had a chance to look at 10 cases across Missouri and Illinois, and in these 10 cases, we found out this convergence signature often extended almost over 120 kilometers in length, with locally enhanced velocity differences along the leading edge of the convective line. And the depth of this convergence zone could be, the average depth was around 6.2 kilometers, with a depth from 3 to 9 at times. The width could be around 2 to 6 kilometers, with steep velocity gradients found along the convergence zone itself. And the magnitudes, basically the velocity differences were between 25 and 50 meters per second. Pretty impressive here. So with our July 2nd case, here's our convective cluster to our west, Columbia being located right in the central portion of Boone County here. And our goal here was to try to forecast the initial onset of damaging winds. How can we improve our capability to forecast damaging winds? We know when the system's blowing out, we got wind damage occurring on the ground. There's no question about that. So we've been looking at this mid-altitude radial convergence signature, and this is a 2258 image from our radar. Now the blues in this case indicates velocities towards the radar. Our radar is out here towards the east here. The reds indicate and oranges indicate outbound velocities away from the radar. So what we do observe is pretty good intense zone of convergence along the leading line through here in this case. And we do get some pretty steep velocity gradients being detected, particularly in the southern portion. This is storm relative velocity information taken at the 0.5 degree elevation angle. We also can look at this in 4 panels, again showing at 4 panels at the same time, looking at 0.5 degrees at low levels, 1.5 degrees aloft. And note, we're looking at a sloping updraft structure. The work that Eric Rasmussen done, the work that Howes has done, shows a sloping updraft structure. Note, again, the outbalance indicates the positive updraft structure. The blues indicate basically the negative anomaly, the negative buoyancy anomaly here in this case. And note we got some pretty intense updrafts here at 1.5 degrees being detected as well. Again, all along the leading edge of the convective line through here. So we keyed upon these very intense regions here where we see some pretty good intense convergence. And we started issuing warnings based on this signature, along with other conventional signatures, reflectivity, as well as the signature called vertical integrated liquid. And we found this to be a pretty good signature, particularly if we have a good viewing angle from the west to from the east to the west. In this particular case, we did. The next volume scan will show you again how the storm did change. It didn't change too much, but again, note the pretty good multi-cell cluster existing to our west, just west of Columbia here. And note this nice, neat little area of intense convergence along the convective leading line. Very impressive, right through this region through here. So we keyed upon this region through here, all the way through this, actually this whole portion, this intense portion of this line here. And we start issuing severe thunderstorm warnings based on this signature as well as other conventional signatures. And we were winning the ball game in this particular case. We able to document this marked signature across Missouri from 2246 on to about 2321. And this is what it kind of looked like. We developed a lot of time height series showing how this signature evolved. And when did we observe the first reports of wind damage? So note in this particular case, this is a time series. This is height up to 10 kilometers. Time began at 2246, extend out to 2332. And we're looking at pretty good intense mid-level convergence across this region across this portion here from 2246 on to 2303. Actually extend all the way through in this whole time period here. And then the wind damage began to commence here at 2309 and well into 2332 and so forth. But all this is occurring prior to the Boeing evolution. That's what's unique about this particular activity here. Another example, and I'll tell you a little story about this one. I gave my little dog and pony show up in Bismarck, North Dakota back 2 summers ago, and around 1-2 p.m. in the afternoon, and 2 hours later they had this particular monster west of them. And that monster produced this type of vertical echo structure. Very impressive. Now you do see a well-defined weak echo region along the leading edge here. Very impressive convective cells up to about 40,000. And what's unique about, here's the mesoscale airflow structure. This is really impressive right here. Again, we're going back to this sloping updraft region. And here's the mesoscale inflow begin to form in the back edge and also, again, develops to the rear with time. And again, our marked signature we're looking at to forecast damaging winds is right through here, around 15 to 18,000 feet. Very intense storm top divergence, a very good strong velocity precursor to indicate intense hail, large hail, as well as also damaging winds. This is pretty impressive cross-section showing the actual mesoscale airflow structures within a developing linear convective line evolving into a bow-echo structure. The other case I'm going to show is the July 15th, 1995 case. And this case moves across northern New York State, produced horrendous amount of wind damage across all portions north of Albany into this northern portion of the state. Very impressive bow-echo structure here evolving, actually evolving through this particular time at 0910. And long and behold, we observe this intense velocity gradient. Again, note the well-defined intense convergence along the leading line here being detected this portion as well as up through here. And we have some very horrendous wind damage occurring across this portion of New York State for the next hour and a half. Next volume scan. Again, a very horrendous, beautiful bow-echo structure. This is incredible. This is really incredible. And no doubt you got very intense reflectivity gradients along the leading edge, little notches on the back side. And again, we're seeing this intense convergence being detected along the leading convective line. This one's almost like a no-brainer in this particular case through here, showing up. Again, the outbounds quite well defined with the oranges and reds here, and the strong inbounds with the blues along the leading edge here. And we did, again, another trace showing how this mark signature evolved. And again, during this intensifying stage, we're going to look at that first trace to the north up here. We see pretty impressive convergence. Again, we're looking at basically the magnitude of the inbound plus the magnitude of the outbound, and add them together basically. This is in meters per second, and we're getting values well beyond 25 meters per second across the whole spectrum here from 0901 through 0926 UCT. So the region of strong outbound velocity signifies a component of the system's updraft current, front to rear flow, when viewing and approaching the storm from the west to the northwest. The region of strong inbound velocity depicts the storm's mesoscale downdraft origins of the mesoscale rim flow jet. And that zone, again, between the updraft and downdraft current is referred to as a rearward sloping zone of negative horizontal vorticity. And what we found out was that the first and second and third circulations often form in this zone between the two drafts, mainly within the updraft current. Basically, when we see this, when vortices do form, they form, again, rapidly within the zone of the horizontal buoyancy gradients along the leading edge here, and they develop in response to the tilting of horizontal vorticity into the vertical and subsequent stretching of the vorticity. What we found out in our study of our 10 cases, the first circulation often forms along the cyclonic shear side or the northern side of the bowing structure. In the early stages, over half of our cases, we found out that the circulation frequently meets mesocyclone criteria during the early stages and exhibited strong cyclonic shears. This referred to as rotational velocities to measure the magnitude of the intense circulation. When we see in weather service, when we observe values around 40 to 50 knots, that's a very strong mesocyclone we're observing. And also, we observe also appreciable depth with that first circulation. On the July 2nd case, this is, again, about 20 minutes after what I showed you earlier, we begin seeing the first stage of the bow echo structure, just west of Columbia. And long and behold, our first circulation begins to form right there, on the cyclonic shear side and the northern side of that bowing structure. And it's a very intense mesocyclone at that time. I was able to do a 4-panel presentation showing this particular at this time. This is at 0.5 degree elevation, 1.5 to the north. Note again, we got strong inbound velocities, the blues against the strong reds, the outbound velocities, very tight, intense circulation up there, and being detected at both elevation angles. This is at 0.5 degree elevation slice, up around 11, 12,000 feet, and the second slice is up around 22,000 feet, 23, at 1.5 degrees. Again, note at the northern portion of the actual bowing structure itself. In this particular case, we were able to trace out that circulation. What we do a lot is to understand the characteristics of a mesocyclone. We look at basically a time-height series of how that circulation evolves. We look at the magnitudes of that circulation, and in this particular case, this circulation developed very rapidly over a deep layer. And this begins at 2309, and this is in kilometers from 0 to 10 kilometers in depth here. Note the circulation is very deep initially, and it intensifies very rapidly. We see rotational velocities of 50 knots, 45, 50 knots within a few volume scans here, and we also have kinetic activity occurring. One of the things in bow echo structures and some of these bowing structures is just a rapid growth of these circulations. I'm really getting kind of scared sometimes when I see a circulation forming, and then 2 volume scans later, I've got a strong mesocyclone producing a tornado. Right? But we have documented this in 3 different occasions. So one thing, and I know in the Weather Service, we're always very focusing our attention on the rapid growth of circulation development within a couple of volume scans. It's just incredible sometimes. In this case, we had weak tornadoes across northern Boone County with that particular circulation up to the north. This time-height series, I'm going to get back to this here shortly. This shows also the diameter of that circulation, the mesocyclone. Note that the mesocyclone diameter is very small early on, around 5 kilometers or less, and then it's going to broaden with time here up to around closer around 20 kilometers. I'll spend a little more time about this a little later. But note, during the time when we have kinetic activity, we have a very tight circulation, very small, very tight on the northern flank of that particular bowing structure. Now in the mature phase of a squall line, we basically see a transition from the intensifying to the mature stage can be marked by the evolution of a bow echo or bowing segments within the larger line. And during the early part of the mature squall line, we began to observe a draft structure gradually tilting to the rear. Basically, we're seeing convective towers begin to tilt to the back. Most of our convective towers in the intensifying stage mainly are vertical in structure with a weak echo region on the forward flank. But with time, in the mature phase, we begin to start seeing this convective towers begin to tilt to the rear. But because of the cold pool with the system cold pools, the downdraft structure is so intense that it's causing these towers to tilt to the back to the west with time here. And we've observed this like in several of our cases here. This is a classic, I know many of you have seen this. This is a classic diagram of the storm conceptual model and mesosphere airflow structure of the MCS. Note this is in the mature phase. We see the multi-cell evolution of the MCS with new convective growth along the leading edge, the mature convective towers, the weakening convective towers, and we see the ascending draft structures. This is referred to as the ascending front to rear flow, and the flow down beneath is referred to as the ascending rear inflow jet. Again, in our cases, we observe that, and also, again, the work done by Klimowski and others have shown that the rear inflow develops at the back edge of these intense convective towers and develops to the rear with time. There are two basic patterns we observe on squall lines. One's referred to as a symmetric pattern, and then a second referred to as an asymmetric pattern, resulting from a very large mid-level low located as an L4 in that location there. We have seen cases where the symmetric can evolve into asymmetric. And the asymmetric is often accompanied by intense reflectivity cores, often along the southern flank, with enhanced strata from precipitation, usually on the northern portion of this line. While the symmetric structure, we see basically a lean convective line, a transition zone of weak reflectivity, and then the enhanced strata from precip region trailing the transition zone. In our July 2nd case, you can see what happens from just within a few volume scans from 2321 to 2338. We began to lose what? The intense reflectivity gradients along the leading edge. Note high reflectivity cores are now displaced to the rear, and we see well-defined bowing structure begin to evolve here with time. Big-time wind damage. I believe there was some damage at the football field, at Farrell Field at the university there. Quite a bit of damage was occurring across Columbia, trees, power lines, as well as some structural damage. Windows were blown out. Wind speeds were over, like, say, 70 knots in some cases across portions of central Missouri and Boone County here. And you know you got intense wind damage occurring. This is the storm relative velocity images. Note the very deep area of intense inbounds. The dark blue region indicates winds greater than 50 knots. But on top of that, the storm motion here is at 32 knots. We combine them, we have over 80 knots of wind blowing towards our radar. So very intense winds all across this whole region through here. And yet here's our circulation number 1 up to the north. And what we observe a lot of times during this particular boreal phase is the growth of secondary circulations. We see a circulation number 2 evolving right here in the southwest portion of Audrain County. Usually after the initial growth of the first vortex, we observe second and also successive vortices may rapidly develop from the apex northward along the cyclonic shear side of the bowing structure. Often these second vortices may originate below 3 kilometers or 10,000 feet and rapidly and deeply intensify over short time periods of 10 to 15 minutes. And we did a trace in this July 2nd case of the circulation tracks. Note the circulation tracks with the northern portion of the bowing structure do traverse mainly to the north and east. Here's our second circulation forming here at 2332. We have weaker cyclonic circulations 2355, 0002 along the northern portion. Now these circulations down south, southern portion of the bowing structure are referred to as anticyclonic circulations. They have often shorter lifespans and they have usually weaker shears compared to the cyclonic members up to the north. And we did a trace of the second circulation here. This one was also tornadic. Again, I'm going to really emphasize, note within a very short time period, 15 minutes, we go from a circulation identified around 3 kilometer, at the 3 kilometer range, and boom, within two volume scans, we see a full-blown mesocyclone, very intense circulation, very intense shears with the circulation, and tornado on the ground. So, you know, if you were trying to do some storm chasing, I mean, goodness, I don't know what, I mean, just if you're in the northern portion, you might, you know, goodness, these things can just happen over a short time period. I know this is a problem for weather service people. seeing these type of traces like this, showing how the circulation evolves over a very short time span is just incredible. And also, again, producing a tornado within a period of 2 volume scans or within a period about within 15 minutes here. And here's the circulation diameter, that's circulation number 2. Again, around 5 kilometers in this case. It remains around 5 kilometers and then begins to broaden at the very end here. As I mentioned earlier, we had several anticyclonic vortices on the southern flank of the July 2nd case. And again, these circulations often have shorter lifespans compared to cyclonic counterparts. The overall depths are smaller. The strongest shears are often detected at mid-levels of the vortex, and vortex diameters do not change much during their life cycle. However, these vortices can enhance the downward transport momentum towards the leading convective line. I'm just going to show you one example of one of the anticyclonic vortices that we were able to detect. And this is a time height trace showing the actual degree of shear, actually the rotational velocities of this case. No, it's more of a mid-level feature for the most part. We don't see strong shears like we observed with our cyclonic members at the lower levels here particularly, but more of a mid-level feature up around 2.5, 3 kilometer range where we observed the strongest anticyclonic shears. Again, when we calculate rotational velocities, we're looking at the magnitude of the inbound plus the magnitude of the outbound velocities, and we divide this by 2. There's that phase in the bow echo referred to as the upshear tilting phase. And Wiseman in his numerical simulations did some work on this where we see the convective Kopu overwhelming the ambient shear. And this is a case where we see basically, again, the convective towers along the leading convective line don't have a chance to fully develop and evolve due to the intense mesoscale rear inflow and also the intense Kopu, which is overwhelming the ambient shear. And here's a case I'm just going to show you at this time where, with this particular case, note that the convective towers are stronger at the ends of this bowing structure, but at the leading edge, we have weaker reflectivities along the leading edge here, for 40-45 dBz, where we have 50-55 dBz at the ends. Yet, we do have intense wind damage occurring from just about this portion here southward along the cyclonic shear side and even south of the apex at this point. But again, the greatest degree of wind damage is occurring right in this fashion through here, right north of the apex northward from that point. And to prove it on the velocity imagery, this shows up very impressive. Again, a big blob of imbalance coming at you. You know this is big-time wind damage. This is horrendous wind damage across this region. Again, we have wind speeds over 80 knots at the surface occurring across portions of Audrain County and east of Columbia through portions of Callaway and also Montgomery County. We'll be coming across this region here shortly. But this is big-time wind damage, this type of velocity signature we observe with the radar. One other thing I should point out is that I'm going to go back to our circulation number 1. This circulation also likely enhanced, if I can dig up my, this circulation also played an important role in enhancing the mesoscale rear inflow, or the intense downdrafts along the leading edge here. This is the convective line at 0013 or 7:13 p.m. that evening. And note at this time, again, we lost a lot of our high reflectivities along the leading edge here. Well-defined weak echo channel being detected in the rear of the convective system. But the velocity imagery does show an impressive vortex up to the north. And this is referred to as a line-end vortex or a bookend vortex here. And this vortex basically enhances that mesoscale rear inflow as well along the leading convective line. Again, our greatest degree of damaging winds occurred just south of this broad scale vortex. This is that first circulation we observed back around, around 2321 over just north of Columbia. And the circulation broadened and deepened here quite a bit. We have also one other cross-section at this time showing how this, the vertical structure of the storms just west of St. Louis here. multi-cell evolution with the new convective towers along the leading edge, multi-cell convection, and the weakening convective towers towards the rear. And we're seeing a nice airflow structure within the convective line. Well-defined front to rear flow, and then intense mesoscale rear inflow jet. And note we're getting values over 64 knots, almost hitting the ground at this particular time. This is a nice sloping, descending mesoscale rear inflow. And again, this is our cause of our damage. Some of this rear inflow, again, does make it to almost near the surface practically, causing a great degree of damage to occur along the leading convective line. This is about 20 minutes later. The line continues to move on to the north of St. Louis. And we're still getting some pretty intense inbound velocities to the north and west of us at 0042 UCT. Again, we're still seeing some 50 knots. This is storm relative velocity information. And again, we've still got some reflection of that vortex, very broad scale vortex up to the north here being detected. And long and behold, my last image right here shows a well-defined Boeing structure beginning to form into its dissipating stages here at this point north of St. Louis. And again, we're losing some of the reflectivity. There's some slight attenuation with it at this particular time. But again, we're still observing some pretty intense wind damage along the leading edge of the convective line here. And the SRM data. The base velocity information, this is base velocity, this is showing pretty intense outbounds now of over 36 to 50 knots along the leading convective line at the last stages of the convective line itself. I want to show you also a little bit about the 715, the July 15th case later on in its life cycle. Remember how intense it was earlier, over almost a half hour ago practically, and at this stage of the game we're beginning to lose the high reflectivity along the leading line. Yet this is still a big and intense wind producer moving across much of northern central New York State. And this system continues to move across into central Massachusetts during the early morning hours after 6, 7 o'clock in the morning. And also note, we do observe a pretty intense vortex up to the north. So you can see that broad circulation being detected. Line and vortex, a bookend vortex, enhancing this intense mesoscale wind flow towards the leading convective line here. And I got another set of images here at 0941, one volume scan later. Note again, the greatest portion of that Boeing structure is being detected up to the north. Very intense wind damage along the leading convective line here. And we see a pretty intense circulation up to the north with that particular comma portion of the echo itself. So the greatest degree of wind damage, again, was occurring just south of this broad vortex, as we observed in this particular case, all across this whole region through here. And to prove that point, we had a horrendous amount of 64 knots coming across much of New York State. I mean, this is a no-brainer. I mean, this is just like, you can almost close your eyes and blindfold yourself, and here it is, practically. So, but this is just big-time wind damage all across much of New York State. And this all occurred during the early morning hours after 3, 4 o'clock in the morning across this portion. I believe there were several injuries and a couple of fatalities in some of the local state parks across New York State in this particular case. Very intense, damaging wind event. Just wanted to show you one example of the circulation, that circulation 1 with this case. We're able to trace the history of its evolution, and there's a very stable circulation. The northern circulation was very stable across the northern portion of the line here that was associated with the comma head. And again, we'll be looking at the actual rotational velocities, showing a very stable circulation. This is in meters per second in this case. And velocities, these are rotational velocities, meters per second. Again, we're basically look at the magnitude of the inbound plus the magnitude of the outbound divided by 2, and we're able to plot these values on the chart here. Note again, we have a time height series from 0901 across to 0936, and a depth of up to 10 kilometers here. Again, a very stable circulation throughout much of its history. And this is also, again, playing an important role in enhancing that mesoscale wind flow towards the leading convective line. Okay. And then the diameter of that circulation, again, was also a very broad diameter of over 20 kilometers across much of its life history here. Okay. Just want to show you the third circulation, the one down to the south, which was anticyclonic in nature, just to prove the point that these circulations don't, mainly the strongest shears basically exist in mid-levels in this case, and again, they also play an important role in enhancing the mesoscale wind flow towards the leading convective line. In our study, we looked at 12 line vortices across Missouri and Illinois, and 7 were cyclonic. 9 were cyclonic, 3 were anticyclonic, and of the 7 cyclonic ones, they originated from a circulation which satisfied mesocycline criteria. Cyclonic vortices often frequently exhibited strong cyclonic shears compared to the anticyclonic counterparts during this stage of the vortex evolution, and the overall diameters at the end was about 15 to 30 kilometers. And observations showing that the strongest area of damaging winds often occurred along the leading cyclonic shear side, and sometimes anticyclonic shear side of the bow, or mainly just southeast or northeast of the line of vortices. So the anticyclonic vortex circulation also played a role, like in enhancing the mesoscale wind flow towards the leading convective line. During the dissipating stage, I won't go into great detail, but basically at this stage of the game, we're seeing basically a deep ascent near the leading edge of the convective line can no longer be maintained, because at this time the system's cold pool has overwhelmed the ambient shear. The gust front surges well ahead of the system, or the precipitation producing inflow has been swept out, swept to the rear over the cold pool system. And the reflectivity patterns at this time basically changes from a fairly continuous large reflectivity along the leading edge to a more scalloped type pattern with weaker discrete cells. And these convective cells are much shallower compared to the earlier convection. So in this whole presentation, I try to key upon the intensifying stage. Our biggest problem early on in the 80s was how can we determine that initial onset of damaging winds? What was the tools we can use, basically? And we found out that using Doppler data, Doppler velocity information, we were able to look at basically this middle-altitude radio convergence signature as a tool to help us out to at least forecast the initial onset of damaging winds. And then also, the growth of the first circulations and second circulations has been very impressive. And again, we've been awestruck, particularly just, these things develop within a period, like say 2 volume scans. Within 15 minutes, we go from a circulation of moderate intensity to a very intense circulation, and then we have tornadoes on the ground within 15 minutes. So we see rapid vortex growth occurring during that intensifying to that mature stage of the bow echo. And again, most of the intense circulations usually often form near or north of the apex, and they evolve, through the whole life cycle, initially producing possible tornadoes, and then, becoming a very broad vortex with time. Paul, how much time do I have?
You want to take questions about
15? Okay. I can, let me just show you real quick. I want to show one more case here for about 5 minutes here, and this won't take too long. But just wanted to show you a recent case where, in this situation, I'm just going to show some images here. Here's a case which occurred back on May 25th, 1996. Again, for some reason, Columbia is a hot spot. I don't know why. But they always get the good weather out there. Maybe it's Raleigh. I'm not sure what but anyway, These people, they always get hit by a lot of severe weather across Missouri, Columbia, into Algerine County and so forth. In this particular case, here's an isolated cell to the east, a line, linear convective line to the west here, moving across this region. And what I want to show in this particular case, here's one of the situations where the circulation was not as intense. Our first circulation, number one up to the north, was not as intense. However, within a period of just right after cell line merger, this is 2142, we get merger occurring. And at the time of merger, this circulation 1 rapidly intensifies. Really interesting. We see rapid growth and intensification. It's a broad circulation. It's not very tight, but it's a broad scale circulation. But that resulted in causing this part of the line to accelerate. We went from maybe 30 knots. We went from 30 knots close to around 40 knots in wind, 40 knot speed in line movement to the east. So that vortex up to the north played a role, and played like a role as a bookend vortex, enhancing the mesoscale wind flow on the backside of this convective system. And on top of that, when that happened, we had chain reaction going. Well, let me just go ahead and show you the trace of this vortex, this circulation here. Here it was, a little bouncing around here, the circulation early on, but after that cell interacted with that line, the circulation intensified. Real interesting. Rapidly intensified and deepened. But it still remained a pretty good broad vortex. Actually, it even became broader with time here. Note the diameter increased after 2148, increased quite a bit, but it still was a pretty intense circulation. But anyway, it caused that line to accelerate, and here's 2212. Another interaction with a small cell interacting with the line here. And now we have circulation number 3 evolving along the apex of that line, of that accelerated portion of the line. And when that happened, we had an intense mesocyclone formed, which became tornadic. And that's it right there, right along the forward flank of that convective line. And that circulation along the apex of that particular line had this type of trace. It also formed at low levels, below 4 kilometers. Again, this is a rotational velocity time height series showing the magnitudes of the rotational velocities. And you can see that the circulation initially formed at the apex of the accelerated portion of the line. It intensified, deepened, and again we have our tornado touchdown occurring just during the time of peak, actually just after it peaked out with height here, and also during the time of intense shears. We had F1 damage about a 5-mile path. It's interesting in this particular case here, where if that cell did not interact with that line, maybe we've never had this whole evolution occurring. I'm not really sure. But it's interesting, when that cell did interact with that line, the first vortex intensified, causing the line to accelerate. This acceleration happened, the second vortex formed, and we have this tornadic circulation evolving. Really interesting. So just a little second case here. I'll stop right here at this point. So and also entertain any questions.
Yeah, I'd like to, for each of the speakers, I'd like to take the time to do some questions. And if you like, there's a couple of slides that might have been good if anybody wanted to see them again. Sure. I would like to point out that a lot of the stuff that, as far as descriptions, a lot of it's online with the Comet studies.
Right, exactly. MedEd and MedEd, yeah. Right.
You want to give the URL for that?
Yeah, it's http:// I think it's meded.edu.
MedEd?
Yeah, meted.edu. Right.
.ucar.
Yeah, UCAR. Thank you very much.
So do you have any questions?
Yeah.
Your first case there, the tornadic activity was right at the start when the squall line in the Boeing.
It was just beginning to occur, right.
Is that a common occurrence? Is that when we watch for tornadoes?
Yeah, we're starting to see that occurring, like say, we're seeing the Mark signature, the radio convergence first being detected, and then like say about 2-3 volume scans later, we're seeing that first vortex evolving just the time when the first bowings begin to show up quite a bit in our cases here. And then the circulation, in over half of our cases, the circulation was a tight circulation initially, and rapidly deepened, intensified, and within 15 minutes, it became a tornadic circulation. This raises gray hair in my head, basically. I mean, very rapid, I think in a lot of supercell cases, you see this intense circulation continuing for many, tens of minutes and so forth. But unique in these cases that we see very rapid growth of these tornadic circulations. And again, everything's occurring along the cyclonic shear side, the northern side of the actual squall line here in this case. So, and this is where we find the greatest degree of damaging winds, usually, like say, from near the apex or just south of the apex northward along the cyclonic shear side.
So is that most tornadoes usually right at the start, once it's gone and then
Right.
expand?
Yeah, exactly. Once it expands, but also plays another role. The second role, again, it's going to enhance the whole mesoscale inflow current, basically, from the towards the leading convective line. So it's playing almost a double role in this particular case here, right? Yeah.
When you say that circulation enhances the rear inflow current, couldn't it be the other way around, that the rear inflow is increasing and causes?
I don't think so. Don't know for sure. I don't think so. I think really we're seeing more of an enhanced. That's true. I mean, one thing we're seeing for sure, when that vortex, particularly that first circulation, begins to broaden, we're seeing the strongest wind damage. This is back to my July 2nd case, and it's right through here. My greatest degree of wind damage is occurring right through here, south and east of that vortex. And here's vortex number 2, right, shown up right there at that point. So, but this is a pretty intense circular vortex here, and again, I'm getting some horrendous wind damage occurring in this portion of southern Drain County and moving into portions of Pike County, western, central, southern, southwest Pike County here. So no doubt, versus true, we are getting wind damage all along the leading convective line, but our greatest degree of wind damage, the highest magnitudes of wind speed are occurring just south of this, referred to as the bookend vortex or line-end vortex region. So that's a kind of a good key I've been looking at quite a bit. So.
John?
I have to jump in here and say that, at least from my perspective, the sense of, which comes first, the vortex or the enhancement of the vortex and the rear inflow, I think those things happen simultaneously. The rotational velocity you're talking about is really a substitute for the vorticity, which is nothing more than a derivative of the flow field. So as the flow field evolves, the vorticity or the rotational flow evolves with it. I don't think one causes the other, they happen together. So I think I would take some issue with your comment about one enhancing the other, and I would take issue with the notion that the other enhances the one. I think they happen together. That's a necessary, in effect, the kinematic property of the flow.
And they're both working simultaneously, side by side.
Yeah, you have
right.
to be careful.
Sure. But one thing for certain, we're seeing the greatest degree of wind damage, often again to the south and east of that vortex. That's been documented, like I say, in several of our cases. It's been really, and also the new additional secondary growth of new vortices forming, again, along that just southeast of the primary vortex there, that location. So.
Ron, from an operational standpoint, you had the development of the first vortex, which enhanced the line, and you had wind damage.
Right.
The second one was tornadic.
Yeah.
How was it warned beforehand?
Well, the thing is, this is one of our early cases, and we had tornado warnings out. I'll go back to Boone County early on, based on that first intense circulation on the northern flank of the line there. Due to it satisfied mesocyclone criteria, we had very deep circulation, very intense, very tight circulation, and with that in mind, we kept issuing tornado warnings in Drain County and also in northern Callaway here in this region through here, based on the fact that we were thinking of the work that was done by Forbes and Wakimoto. Their great work done back, they had a couple good cases. They observed the 1982 case across central Illinois. They observed the bowing structure. And with that particular case, that was in the back of our minds, saying that, yeah, we could probably see the growth of potential new circulations evolving, genetic circulations evolving. In real time, it was difficult. I mean, this is one of the problems, things that happen so rapidly over a short time period. In real time, it was very difficult to discern, and particularly, like I say, in this case, is one of our first cases. However, in our other cases we've been looking at, we were able to detect that second and third successive circulation. And if it met shear criteria, if it met depth criteria, if it met the second criteria, we issued tornado warnings in that regards, or it can be severe thunderstorm warnings in this case. So, yeah.
Regarding these cases where you've got the rapid vortex spin up along the leading shear plank, have you noticed in all the cases that you've looked at, there's a higher tendency or percentage of cases in, say, higher shear environments, or that does a higher shear environment tend to promote that, or is there any difference?
No, most of our cases, if I want to define shear, environmental shear, for example, okay, I'm looking at the environmental shear in our cases, we look at the mean layer, 0.3 kilometers, what's the delta V, basically, in the environmental shear, and we're looking at values around 15, 17 meter per second. That's been kind of standard. So in our stronger cases, like if we had shear maybe 20 meter per second or 22 meter per second shear within that layer, we haven't had too many of those cases. Most of our cases fell in that, I kind of call moderate shear category. And they were producing intense circulations. We did have some very good turning of the wind field within the lowest kilometer that was observed in our VWP information, of velocity wind profile information and so forth.
Was there any differentiation between that and line normal shear?
I'm sorry.
The shear perpendicular to the line before the fault formed?
Yeah, some, not too much really, not too much for the most part. So one thing I like to point out is that it's interesting to point out in our cases, like say in this case, the first circulation, I should point out, also formed near the east-west frontal boundary. So you got local vorticity near that boundary. I'm not sure how much that helped, assisted in that particular process of helping that vortex there, but the east-west frontal boundary, or it could be an old outflow boundary, was present there. So it could have tapped the local vorticity from that boundary, and hence that first circulation there in that regards as well, the northern portion. Yeah.
What typically was the shape of the photograph in the lowest 3 kilometers? I thought earlier you said it was...
Mainly linear, except for the lowest, maybe like say in a lot of our cases, the lowest half of 1 kilometer could be curved. But beyond that, it's pretty linear in nature. Above that, basically linear in character for the most part, with increasing wind speeds with height. So.
Other questions?
Yeah.
I'd like to know if it's possible that anticyclonic cyclone, is it strong enough to produce the rare anticyclonic tornado?
No. Again, the anticyclonic circulations are weaker. They're not as strong as the cyclonic members in our cases. And basically, they're more of a mid-lower feature rather than being a very deep feature. So if anything, they're kind of working, basically enhancing, maybe I would say working with the actual flow field itself together, but there was no kind of kinetic activity with the anticyclonic circulations at all, for the most part. Mainly, like I say, the cyclonic members were the ones that were producing the tornadoes. So I'm really interested to see, and down the line, if you do observe squall lines or observe a line across Illinois, Wisconsin, the Midwest here, what do you observe, like, say, if you were to the northeast of this line? Are you able to observe any kind of tornadic activity? We get a chance to go out. I'm going to pitch out the fact that we do get a chance to go out to do damage surveys and see what actually occurred on the ground and compare it to the radar information we observe in our scope, in our screens and so forth. And we try to do the best we can, do some detailed damage surveys and really find the tracks of the tornado tracks associated with the squall lines. And these are tough. I mean, these are not easy because you have damaging winds occurring, damaging downburst winds, and you're trying to observe actual tornado tracks associated with the convective lines here in this case. So,
I have a question, Ron, about the tornadoes. it seemed like some of the reflectivity that you were showing of some of the tidal circulations that produce tornadoes didn't have much reflectivity north of that area. Is there any spotter reports of like location of where the tornado might be, or how spotters would deal with any of that? Because it doesn't look like your typical...
No, basically in this situation, we're talking about basically non-supercell tornadoes occurring on the northern flank of that line there for the most part. And spotters have observed, you know, we get reports, like say in this May 25th case, we had 2 spotters reported a tornado with that circulation along the leading convective line there. It's amazing. But they were able to just, we received reports of actual tornadoes on the ground for a period of over, like say, 2 different instances for over that 5-mile track there. So this is a really precarious area. All these finds are on the, I call this kind of like the early stages still. I mean, we need to look at 20, 25 cases. 10 cases is not enough to really make some definitive statements. Basically just some observations here for the most part, saying it was what we're observing thus far. But it's really a fascinating area, I think. One thing I like to point out, I think we kind of proved Dr. Fujia's work about the rotating comet head up to the north in this regards. And also he talked about the tornadoes occurring near the apex or north of the apex of the Boeing structure. I think we validated some of Dr. Fujia's work here. I mean, just basically, yes, we observed on Doppler data that the circulation involves just north of that spearhead portion of the echo. So it's really, it's nice to see that we can, you know, we're seeing on Doppler velocity data, seeing what was shown, like I said, what Dr. Fujia has done back in the 1970s here.
Time for one more question. Yeah.
Mathematically speaking, how many times do you think a spotter might see a meso spin up on the front end in an associated tornado?
Not too often. He's got to be in the right location, the right time. Okay. Because these are short-lived tornadoes. Now, it so happened that this one tornado on May 25th did have a 5-mile track. But generally speaking, these are very short-lived tornadoes. And if he's at the right location at the right time, yeah, he may capture it. And we have had reports come in from the amateur radio people, from the local spotter groups. They have been a big help in helping us out. And we've gone out to do damage surveys the following day and verify this. And we were able to verify it. It's really impressive, really. So, yeah, the spotter groups are really, I mean, no question in my mind, they're a very strong asset and needed to help us out, no question.
Do you think that the potential for this to exist is enough that we want to look at changing our tactics from years past when we always taught precipitation leading, meso in the centering, cloud-based trailing, the typical theory?
Or a typical supercell evolution you're referring to, basically? No. I mean, just, you know, if something's coming towards you, we hope that, you know, chances are if you're in the, you know, southeast of the supercell, I mean, you're in the right location to discern a possible tornado, you know, and so forth. In this situation, we try to alert, you know, through the amateur radio, we try to help our folks out in St. Louis. We'd say, do you have any spotters out in this portion of the county that you can contact, help us out? We think there might be some possible tornadic activity occurring. Do you observe anything out there possibly? So it's a two-way communication going on for the most part. But no, I mean, by all means, I mean, I think it's tough on your part. You know, is it a supercell? Is it a squall line coming at you? You know, a squall line has a very deep shelf cloud approaching here for the most part. But what's unique in our cases here, we observe these spin-ups occurring along the leading convective line. And it's amazing in these cases that in the May 25th case, we had deep circulation. I mean, you know, but again, this is all preliminary observations. We need a lot more cases to really do some more good validation of work here in this case. So
I think it underscores, from a spotter perspective, it underscores the necessity of getting spotters thinking, I'm not out there spotting for tornadoes always.
Right.
We need information on wind damage, on large hail. If you're north of that Boeing structure, and I think that's information that should be given out, that we're concerned with high wind damage in this area, and to the north we want to make sure that we've got spotters there. But just keeping in mind that not everything a spotter sees is going to be textbook. And I think we'll talk about that some on Saturday. Life is not, you know, a typical diagram. Rain, hail, and then tornadoes. Life is different than that. This underscores that.
Yeah, the water is very muddy out there. I guarantee that. It's not always a clean, classic. I mean, no offense to the high plains, but the thing is, it's, you know, out this Midwest here, you got a lot more haze, you got poor visibilities. You're not going to see, you know, things are not as easy sometimes. You're not going to, again, like I say, I know we're going to try on the NWSI house to help the spotters out there identify potential locations where we have maybe the greatest degree of wind damage or possible tornadic activity But otherwise, no question, your information is extremely important for us. No question about that. So,
Yeah, I'd like to thank Ron.
yeah. Thank you very much. Appreciate it.
I'd like to encourage that if people have further questions that they'd like to ask Ron or other speakers throughout the event, that please feel free to ask them. That's part of the reason they're here, is we want to make sure that you understand this as an educational experience. As part of that, I wanted to ask a question. Just raise your hand if you are a graduate student in meteorology right now. Okay. And how about undergrads? Those of you who are undergrads, how many are seniors? Okay. How many of you undergraduates, or I guess grads, any of the students, how many people have had courses in understanding, interpreting radar? Okay. How many people think that they should have more in their curriculum? Okay. Something I'm going to encourage you to do is I'd like to, sometime, especially tomorrow, once we get into the swing of things at lunch, at the banquet tomorrow night, I would like to hear from you of things that you would like to see more information incorporated into your curriculum, because I'm very interested in knowing what exactly is being taught to you. I think what Ron has been giving here has just been some phenomenal information. There was a picture, and maybe you could show it just really quickly, Ron. It was the one that you had the great divergence aloft and you had the rear inflow jet.
Yeah, this is...
Being able to understand these diagrams are part, I mean, that's part of the process, and I think that for those of you who are educators here, teaching the student to think is a good idea, and showing them examples like this really help that. I hope you can get that online somewhere, because I would die for that picture. Well, maybe not die, but suffer greatly. You know, it's things like this that I think are just phenomenal. And I'd like to encourage anybody who's got great examples like this to put it on the web, and then I'll even work to help collect them and try to incorporate them into some education that you can get, if not in a classroom, at least online. So I want to hear more of your opinions. We're going to be taking a break here before we get to Greg. Rob, Dale, I got an announcement for you. I've got good news and bad news for you. The good news is they found your luggage. The bad news is it's in Detroit. So so you are requested to call the airline, all right? At this time, we're going to take just about a 15-minute break here. It's about 20 till. Oh, big time important news event. Big time. If you were here for the shelter workshop, you got your lunch ticket and your banquet ticket. If you got it again tonight, you've got somebody else's lunch. All right, so please, if you double registered, if you took the morning class and then got another folder here tonight, please go to the desk. Rich, see everybody say hi to Rich. Please give him your extra tickets, because we need those back, because some people aren't getting lunch tickets and they should have. So why don't you go ahead and take about 15 minutes, about 5 till, come back in. Off to your left is the Coke and cookies.